Okay, so welcome back. This week we have only one class, right? So this Friday is a holiday, October 2nd. So after this class, we'll meet only next Wednesday. Okay, and I think there was a few messages about midsem also. We will discuss during our anyway towards the end. We discuss various things. At that time, let's discuss about midsem exam also. And now we can start the class. I will start sharing the screen. Could you please confirm that it's visible?
Yes, sir. Achievable.
It's okay? Yeah, good. Okay, so let's start. Uh, Today we will do two small lemmas. These are actually we could have done these soon after maximum modulus theorem. But I thought we will do it whenever we need it. We will need some of these ideas in the proof of Riemann mapping theorem. So Schwarz lemma and a generalization called Schwarz-Pick lemma. So that's what we will do today. So last time we introduced the concept of, do you recall the word? What did we do? We introduced what is called something that you already knew, but maybe not this word, concept of normal families. So what did this mean? This is a collection of functions, and you say that the family is normal if you take any sequence from there, then it has a subsequence that converges. And we mentioned that the limit need not be part of the family. Okay, and the most important theorem here is something that you have done several times, at least twice, once in real analysis and once in differential equations, called the Azela-Ascoli theorem. And we recall the proof of it once again. So Azela-Ascoli theorem would say that if you have a collection that is point-wise bounded and also equicontinuous, then it is normal. And we proved this. We recall the proof. You had already proved this. We recall the proof. And the two key things to remember was that you need to be in a so we proved that it has a subsequence that converges, and the convergence is good in the sense it's uniform on compact subsets. Okay, this much we need for normal family, and this is what we proved for Azela-Ascoli theorem. So the proof had one or two basic things to remember. One is that if you are in a metric space, to start the proof, you need this to be separable, meaning it should have a countable dense subset. We were working with a region in C, so we can take the subset of those points with real and imaginary parts being rational. So you get a countable dense subset. So that part is there. And then using that, we did what is called a diagonal process in order to construct this subsequence that converges. And we also check that the convergence is uniform on compact subsets. Yeah. So this we recalled, and as an application, as a corollary, we did Montel's theorem. So Montel's theorem will say that if you have a family of holomorphic functions on a region, and if you assume locally uniformly bounded, given a compact set K, this family is uniformly bounded on that K, locally uniformly bounded, then you can show that it's normal. So what you want is, so locally uniformly bounded for free gives you point-wise boundedness. And in order to apply Azela-Ascoli, what more you need equicontinuity. And equicontinuity we deduce from this locally uniform boundedness. This is where we use the compact exhaustion and Cauchy integral formula. So via Cauchy integral formula, you deduced using locally uniformly bounded. You deduce that the family is equicontinuous, and therefore Montel's theorem follows. So quickly recall the keywords in Ascoli. You need to start the process, so you need a countable dense subset. And once you have that, what you do is what is called the diagonal process. That settles Ascoli. And in Montel, you are taking compact exhaustion, and for if you have a collection F, for each function small f in capital F, restricted to, so you restrict the family, each function to Kn, and you show that they are equicontinuous. You show this for each Kn for each n, and you will get corresponding sets of indices S1, S2, etc., one containing the other. We chose it that way. And then we have to do a further diagonal process. So using Ascoli diagonal process, you get S1, S2, S3, etc. And on this descending chain, S1 containing, S2 containing, etc., you do a further diagonal process to conclude Montel's theorem. Today, we could have started, so normal families and Montel's theorem and all we did in order to prove Riemann mapping theorem. We could have started the proof, but I will postpone it to the next class because I am not sure I will finish it in one day and I don't want a long gap. So Friday is a holiday, so let's start after that. Also, what I am doing today, anyway, we need in the proof. So my original idea was to start the proof, and when we need what we are going to do today, Schwarz lemma kind of thing, at that time, make a quick. Anyway, these are not difficult. It follows easily from maximum modulus. I was going to quickly recall these things when we need it. But now that Friday is a holiday, I don't want to start Riemann mapping theorem, so I will spend a bit more time on Schwarz lemma and Schwarzschild. So today we will do a couple of applications of MMT, and this is what we will do, Schwarz lemma. And Schwarzschild I will just state and I will leave it as an exercise. So as usual in the discussion session at the end, we will discuss whatever questions you have, and I think you can also tell me what you like to do for the midsem. I think my own feeling is, all this proctoring using video camera and all that, it's too complicated. So maybe, we will skip midsem. This is what I feel. If you're also comfortable with it, we can have a number of assignments using Google Forms. This is what my preference is, because there was an email recently saying that certain other things that they were thinking of in terms of proctoring via video conferencing, that also may have some difficulties or something like that. I didn't pay much attention. So unless all of you really want midsem, we will not have a midsem, but we will discuss at the end of the class. Okay, so let's start today's topics. So Schwarz lemma is a lemma about the open unit disk. So all Z in C such that mod Z is strictly less than 1. Open unit disk strictly less than 1. And this is just a notation. H infinity is the set of all bounded holomorphic functions on U. Holomorphic functions on the open unit disk, assume they are bounded. So then you can introduce this norm. Norm of F is supremum of mod fz, z in U. This supremum exists because you're assuming that you are considering only bounded functions, therefore supremum exists, and denote the supremum like this. So, H infinity is a famous space. I mean, there are HP spaces and this is P is infinity, and these are all nice non-linear spaces, Banach spaces, but we don't want all that. I just use the notation because these are important spaces. Okay, so this is the norm, supremum of mod xz, and supremum exists because we are considering only bounded functions. Now, what does Schwarz lemma say? So it's a very nice statement. It says that if f is a bounded holomorphic function defined on the open unit disk, and assume that this supremum is less than or equal to 1. So mod fz is less than or equal to 1 for all z in U. Assume that much. Then you can say something more. That's what Schwarz lemma says. So if you have a bounded holomorphic function, and if mod of fz is less than or equal to 1 throughout the open disk, then you can say, so you know that mod fz is less than or equal to 1. This is given to you, but you can say more. assume f of 0 is 0 also, then you can say mod that mod f z is less than or equal to mod z for all z in U. Right? What is given to you is mod f z is less than or equal to 1. You are concluding a bit more using maximum modulus theorem. We will see the proof. And we are going to claim that mod f z is less than or equal to mod z. Have you done this in 421? Maybe you have.
No, we had not. We had not done that.
You have done this, right? So this is
No,
just
no,
no. Are you saying no or yes?
no, no.
No, okay. So this could have been done. I think if lockdown was not there, most likely you would have done this because this doesn't need any advanced thing. It needs only MMT. In fact, when I taught 205 once, I did do this. So for all z in U. So statement is clear, no? From mod f z is less than or equal to 1, with this extra condition, you are concluding that mod f z is less than or equal to mod z. So that's much better. So you are going to conclude. You can also conclude that f prime 0 also has modulus less than or equal to 1. So Schwarz lemma is both these statements together with one more statement. Moreover, if equality holds. So if equality holds either here, suppose mod f prime 0 is 1 or mod f z equal to mod z at some point other than 0. If equality holds, then f has not too many options. Fz has to be a multiple of the identity function. Fz has to be z up to a multiple lambda z. But if fz is lambda z where lambda is a constant, then modulus of lambda has to be 1. Right? That's clear, no? Because you have this condition, right? Mod f z is less than you have this condition. You are assuming that the equality holds. So mod f z is mod z. So mod of lambda z is mod z. Therefore, mod lambda is 1. So so if it's a scalar multiple of the identity function, the scalar multiple is supposed to have modulus 1. So this solves this. Okay, so this is what we have to prove. So the next slide has the proof, but the proof is very easy if you remember the key thing. So the only thing that you need to remember is you consider the function f of z divided by z. That's all that you need to remember. Okay. You consider the function f of z divided by z. So that is not holomorphic on U, no? That is not holomorphic because z equal to 0 is a problematic point. So you have to ask, is it, so it is a singularity. So first of all, you ask, is it an isolated singularity? Of course, it's only an isolated singularity because if z non-zero, then fz by z is fine. So it is isolated. Next question is, you know that isolated singularities come in 3 types. So which type is this? So what type of an isolated singularity is this at z equal to 0 for the function fz by z?
Removable.
Removable. That is because f is given to be holomorphic throughout U, right? Therefore, and f of 0 is 0. So limit z going to 0, fz by z exists. It is just f prime 0. So it is removable. And therefore, by removing, you get a holomorphic function and you argue with that holomorphic function. You apply MMT to that. That finishes the proof. So proof is consider fz by z. Z equal to 0 is a removable singularity. Remove it and call that function g and apply MMT to g, and that's the proof. So let's see the proof. It is removable. So therefore, there exists a function g which is holomorphic throughout U such that fz is zgz, right? I am calling gz as fz by z, z not equal to 0. And what is g at 0? I need to define g throughout U. So g at z not equal to 0 is fz by z. When you remove, what is g at 0? What should
F
be
prime 0.
f prime 0, right? That's how we remove the singularity. You take f prime 0. So g of 0 is f prime 0. So that will also, come to the, so that's where you will get this condition. G at 0 is f prime 0. And g of z is fz by z. So both these things are together proved if you prove that mod of gz is less than or equal to 1, right? Mod gz less than or equal to 1 gives you this and gives you this also. So what we need to prove is this function g, you have to prove not just mod fz less than or equal to mod z, the other condition also. mod f prime 0 less than or equal to 1 also. Both these will prove, both these will get done if we show that mod of gz is less than or equal to 1. So this is what we need to show. So take z in u and pick an r which is strictly between mod z and 1. So and then apply MMT. So by MMT, so MMT is this statement that if you have a function which is holomorphic throughout a disk DAR bar, right? Because you have taken R strictly bigger, it is throughout the closed disk with radius mod z. You will actually, I mean, the statement that we proved will say that g of 0, mod g of 0 is less than or equal to maximum at theta mod of g r e power I theta. This is what we would have proved, but as a corollary, we deduced that there is no local maximum. G is holomorphic and it has no local maximum. So if you take the disk with centered at 0 and radius r, if you take the closed disk with radius 0 and centered at r, then z is inside that disk and there is no local maximum. So mod gz is less than or equal to this. Maximum theta g of 0 plus r e power I theta, where r is this. Okay. And you also know that equality holds precisely when g is a constant. This was also part of MMT. So g has no local maximum. So you get this inequality. And for each r, you get this inequality. And this is inequality precisely when g is a constant. And what is g? G of r e power I theta is f of r e power I theta by r of e power I theta. So taking modulus, this is maximum modulus of f of r e power I theta. There's a bracket missing here. Divided by modulus of r e power I theta, which is just r. But one condition that is given to you, what is the hypothesis on f? If you have this condition that the norm is less than or equal to 1, meaning mod fz is less than or equal to 1. For each z in u, mod fz is less than or equal to 1. Therefore, here, this is less than or equal to 1. And this r is r itself. So this is less than or equal to 1 by r, since we know that norm is less than or equal to 1. So you have shown that by MMT, you have shown that this function that you are considering, gz, mod gz is less than or equal to 1 by r. This is true for any z in u. So by tending r to infinity, by letting r going to 1, right? You can take r bigger and bigger, and for all that, this is true. So by letting r tending to 1, you would have shown that mod gz is less than or equal to 1 for every z in u. This is what we have to show. So if z is not 0, you would have shown mod fz by z is less than or equal to 1. Therefore, mod fz is less than or equal to mod z. If z equal to 0, g0 is nothing but f prime 0. So you have shown that mod f prime 0 is less than or equal to 1. So g0 is f prime 0. So this also follows. Now, if mod gz is equal to 1 for some z in u, then the maximum is attained, right? Because the maximum of this is 1 or something less than 1. So if mod gz is equal to 1, then the maximum is attained. Locally, a maximum is attained inside, and therefore you can conclude that fz by z, the function gz, has to be a constant. So g is identically a constant lambda, and that shows the statement. If mod fz is mod z, or if mod f prime 0 is 1, then that means g is attaining a maximum inside, therefore g is a constant. So if g is a constant, then mod fz by z is a constant, therefore fz is, g is a constant, so fz by z is a constant, therefore fz is lambda z. So lambda z, mod lambda is 1. Mod lambda is 1 is automatic. So this is a proof of Schwarz lemma. It is a simple application of maximum modulus theorem. Okay. So this proves Schwarz lemma. So this is again maximum modulus theorem. And now let us do something about, so you take the open unit disk and you would like to know what are the biholomorphic functions on U. Meaning, this is what I call automorphisms of U. So these are holomorphic functions from U to U, right? A function on U, a holomorphic function on U can take a value which is outside U. I'm not interested in those functions. I'm interested in those holomorphic functions which take U to U and bijectively, injection and surjection, and inverse is also holomorphic. So this will be an automorphism. So what are those automorphisms? So now we can analyze that using these ideas. So you choose alpha in U to start with. We consider a collection of functions which are automorphisms. Okay, and then we will say that basically they are all the automorphisms. Okay, question is clear. You would like to know what are the biholomorphic mappings of biholomorphic self maps of U. Holomorphic maps from U to U, bijection, inverse is also holomorphic. So let alpha be a complex number such that mod alpha is strictly less than 1, and then define a function phi alpha. Phi alpha at z is z minus alpha by 1 minus alpha bar z, where alpha is with mod less than 1. So these are examples of what are called Mobius transformations. We may come back to Mobius transformations in general later when we give a proof of the Picard theorem, much later. But this is an example of a Mobius transformation. So a general Mobius transformation will look like AZ plus B by CZ plus D, where A, B, C, D are complex numbers. So here A is 1, B is minus alpha, C is minus alpha bar, and D is 1. AZ plus B by CZ plus D. So consider these functions, and I'm not doing it on the slides, but you check. So for alpha, minus alpha is also in U, no? Mod alpha is less than 1, mod minus alpha is less than 1. So phi minus alpha is also there. You check that phi minus alpha composed with phi alpha is the identity map. So phi alpha of z you take, this is the definition. Now you take phi minus alpha of this, you will see that that's nothing but z. So this I leave it for you to check. I'll make this observation that this is equivalent to checking that the product of these two matrices is a scalar matrix. You will see. So if you take A1z plus B1 by C1z plus D1 and A2z plus B2 by C2z plus D2, their composition is nothing but the corresponds to the product of the corresponding matrices A1 B1 C1 D1 times A2 B2 C2 D2. You can check this. So just verify. So you can do this anyway, and therefore what do you conclude? You conclude that, see, right now it is defined for any complex number. Maybe there is a pole or something, but it's a meromorphic function, it's a rational function. But the point that we will observe is if z is in U, then it is holomorphic on U. Because what is the only pole of this function? The only pole of this function is this becoming 0. That is 1 equal to alpha bar z. So the pole is 1 by alpha bar. But if mod alpha is strictly less than 1, then 1 by alpha bar has modulus strictly bigger than 1. So if z is in U, then this is holomorphic. So this is holomorphic throughout U. Okay, but we are yet to come there. From this itself, you can conclude that phi alpha is 1, 1, right? If phi alpha of z1 is phi alpha of z2, then applying phi minus alpha, you get z1 equal to z2. So it is 1, 1. And not only that, phi minus alpha is the inverse of phi alpha. So phi minus alpha is its inverse. So this much you have checked now. Now, if you take a real number, now I'm going to claim two things. I'm going to claim that phi alpha takes, so U is the open unit disk, mod z is strictly less than 1. I'm going to claim that, but this phi alpha is defined for any z, right? Except z is 1 by alpha bar. As a holomorphic function, it is defined for any z except 1 by alpha bar, because mod alpha is strictly less than 1. 1 by alpha bar modulus is strictly bigger than 1. In particular, phi alpha is defined on U bar. There's no problem. Okay, so on U and on the boundary of U, phi alpha is defined. We are going to claim that phi alpha takes a boundary of U to the boundary of U. Phi alpha is a phi alpha takes phi alpha maps boundary of U onto the boundary of U. That's one claim. And next claim is phi alpha maps U onto U. So it maps U onto U and the boundary of U onto boundary of U. So first we will prove it for the boundary. So for this, take T in R, and now you consider Z to be e power it. So that's the element from the boundary of U, right? E power it has modulus 1, so that's from boundary of U. And take phi alpha of e power it, that is e power it minus alpha by 1 minus alpha bar this. So this modulus is equal to this e power it minus alpha by, you multiply by e power minus it. You can multiply by that because that is modulus equal to 1. So e power minus it minus alpha bar. But this is nothing but the bar of this, no? If this was Z, this is Z bar. So the modulus is equal to 1, right? Mod of Z by Z bar is 1. So from this, what do you conclude? If you take something from the boundary of U, then the image is also on the boundary of U, right? Something from the boundary of U will be e power it, and phi alpha of e power it also has modulus 1. So you have concluded that phi alpha maps boundary of U to itself. This is true whatever alpha you have chosen with mod less than 1, modulus less than 1. So now what did we prove? We proved that phi alpha of boundary of U is contained in boundary of U. Phi alpha of boundary of U is contained in boundary of U, and I'm going to conclude that from that you can conclude that phi alpha of boundary U equal to boundary of U. From containment you can conclude equality because of this identity that we know. Phi minus alpha composed with phi alpha is the identity, right? So if you take Z in the boundary of U, you have to show that it's an equality. So you have to show that it's onto. So if you take Z in the boundary of U, then Z you can write as phi minus alpha of phi alpha of Z. Because Z is in the boundary of U, phi alpha of Z is in the boundary of U. So phi minus alpha of an element in the boundary of U is this Z. So it is onto. Is the proof clear? From this identity, from the containment, it follows that it is onto because of this identity. If you take Z from the boundary of U, then it has a pre-image phi alpha Z under the map phi minus alpha, and phi alpha of Z is in the boundary of U, and therefore phi minus alpha maps this to Z. So what you have shown is phi minus alpha maps, phi minus alpha is onto, phi minus alpha is as a map from boundary of U to boundary of U is onto. And this is true for any alpha, so you have shown it for phi alpha. Okay, so in order to argue generally, maybe I should have written phi alpha or phi minus alpha, doesn't matter, it's for any alpha. Okay, so it follows that phi alpha of boundary of U equal to boundary of U. If Z is in the boundary, you have to show that it is a pre-image, and my claim is that phi minus alpha. Yeah, so maybe I will change this. Let this be alpha and this be minus alpha. Okay, so phi minus alpha of Z is a pre-image, and phi minus alpha of Z is a pre-image, and that is phi minus alpha of Z is in boundary of U because Z is in boundary of U. Phi minus alpha maps boundary of U to itself. Okay, now we are going to claim that phi alpha maps U onto U, U onto U. So we have observed already that it's a holomorphic function because mod alpha is strictly less than 1. So 1 by alpha bar is outside U, so it's a holomorphic function. Therefore MMT applies. It's holomorphic on U, so MMT applies, and you can conclude that phi alpha of U is contained in U. Why is that? Because you will get, you know that phi alpha maps boundary of U to itself. So modulus of phi alpha on the boundary is equal to 1. On the boundary, the value is 1. Therefore, in the interior, the value has to be strictly less than 1. Right? What does MMT say? There's no local maximum, and if equality is attained with a boundary value, then it has to be a constant. And phi alpha is not a constant function, clearly. So because it's not a constant function, interior, the value should be strictly less than the boundary value. Strictly less than the boundary value. So phi alpha of z modulus has to be strictly less than 1 by MMT. Therefore, this is contained in U. So this is MMT. And therefore, the same argument applies. Because you have this identity, if you take something from U, if Z is from U, you can write it as phi alpha of phi minus alpha of Z. And phi minus alpha of Z is in U. So you have proved the same argument here shows that phi alpha of U equal to U. Right? If you take Z in U, write Z as phi alpha of phi minus alpha of Z. And phi minus alpha of Z is in U because Z is in U. So you have got a pre-image in U. So this follows. Okay. So what we have shown here is that if you consider this function, then this function has the property that it maps the boundary of U onto the boundary of U, and it maps U onto U. This is what we have observed. Let me go ahead and so therefore these are is it clear that this is a bijection? So you just have to say that this is 1 1, but we have shown that this is 1 1. Phi alpha is also 1 1. So now we have shown that phi alpha of U is U. It is onto U. So phi alpha is a bijection. And once you have a bijection, then inverse is holomorphic is automatic, right? Because we have proved long back, soon after proving, when we were discussing open mapping theorem, we had also inverse function theorem. And you know that, and as a corollary, we have proved that if you have a 1 1 function, you remember this, in order to prove OMT, we proved something like if f vanishes somewhere, right? There was some discussion about m to 1 being, no? If some multiplicity is m, then the map is m to 1, and as a corollary, we proved that if a function is 1 to 1, if a function is 1 to 1, then the derivative is never 0. If on omega, if a function, holomorphic function is 1 to 1, then the derivative is never 0. We have seen that, and because of that, by inverse function theorem, it follows that inverse is holomorphic. So if you have a 1 1 function, then on the range, it has an inverse, and inverse is automatically holomorphic. So we have done this long back. And because phi alpha is 1 to 1, so these functions are 1 to 1 on to U. Therefore, on U it has an inverse, and inverse is automatically holomorphic. In fact, you know the inverse. Inverse is again a function of this form, so you don't need that. I mean, you can conclude that it's holomorphic directly. You don't need the inverse function theorem here. We will need the inverse function theorem in the next argument, not here, because here the inverse is again a function of this form, right? The inverse of this function is this function, phi minus alpha, which is again of that form. So these are automorphisms. So what we have shown is these are automorphisms of U. We are going to show that these are essentially all the automorphisms of U. Okay. So what we have verified now is by MMT that these are automorphisms. By MMT because we used MMT here. So by MMT we verified that these are automorphisms of U. Now we are going to do an argument using Schwarz lemma to show that these are essentially all the automorphisms. So let's do that. So let us take two elements, 2 points from U, alpha and beta, and suppose f is in H infinity. Recall what is H infinity? So these are holomorphic and bounded holomorphic functions defined on the open unit disk. And assume that the norm is less than or equal to 1. So you're assuming that mod fz is less than or equal to 1 for all z in U. Okay, so Rudin makes a remark soon after doing all this that there's no assumption on how the behavior of f is on the boundary. Right, in many results you will assume that f is continuous on the boundary. There's no such assumption here. It's a very powerful statement that we are showing that f is given to be holomorphic on U. On the boundary of U, you know, f can be funny, f can be crazy. We are not assuming anything. We are only assuming that its supremum is less than or equal to 1. There's no continuity condition or anything on the boundary. And this supremum is also on U. F is a bounded holomorphic function on U, therefore supremum exists on U, and that we are assuming is less than or equal to 1. Nothing to do with the boundary. Okay. And also assume these 2 points are given. No, you assume that f takes alpha to beta. So suppose f be any holomorphic function on U bounded with supremum less than or equal to 1 taking alpha to beta, then you consider this function, composition of 3 functions. You take phi minus alpha, compose with f, further compose with phi beta, and observe the properties of this g. First of all, g is in H infinity because f is a bounded holomorphic function on U. Phi minus alpha is a bounded holomorphic function on U. Therefore, this composition is bounded holomorphic on U. I mean, this composition makes sense because phi minus alpha is of z is in U. Therefore, f takes values there and f takes values there, and phi beta takes value on that, so that's okay. And because mod of fz is less than or equal to 1, phi beta of z will make sense on fz. So this makes sense because of this condition. Because mod fz is less than or equal to 1 for all z in U, phi beta can be applied on this thing. It makes sense. And you get g, and you also see that mod gz is less than or equal to 1. Right? Because phi alpha of z is modulus is strictly less than 1. F of that modulus is less than or equal to 1. And therefore phi beta of that modulus is less than or equal to 1 because phi beta takes boundary to boundary and U to U. So modulus is less than 1 if it's U. On the boundary it's equal to 1. So in general it's less than or equal to 1. So less than or equal to 1 is still true for G. It could be 1 also because on f might take value 1. So if f takes value 1, then phi beta takes that to the boundary. So the boundary value also is 1. So it could be 1 also, but anyway, it's at most 1. So you have shown that g is in H infinity and the norm of g is less than or equal to 1. And what is g of 0? Can someone quickly tell me what is g of 0? Recall, phi alpha and phi beta have a certain form. Phi alpha is z minus alpha by 1 minus alpha bar z. So g of 0 is, you have to take phi minus alpha of 0. What is phi minus alpha of 0? Phi alpha of z is z minus alpha by 1 minus alpha bar z. So this is phi minus alpha of z. So that will be z plus alpha by 1 plus alpha bar z and z equal to 0. So the answer is?
Just alpha.
Just alpha. And what is f of alpha?
Beta.
Beta. And what is phi beta of beta?
0.
0. So g of 0 is 0. So you are in the Schwarz lemma situation. You have a function with this property and g of 0 is 0. Therefore Schwarz lemma applies to g. So by Schwarz lemma, what can you conclude? By Schwarz lemma, you have 2 conditions. One is mod g set is less than or equal to mod z, and the other condition is mod g prime 0 is less than or equal to 1. So we are going to use that. Mod g prime 0 is less than or equal to 1. Remember, we could have also used mod g set is less than or equal to mod z. We will get something else, and that is called Schwarz-Pick lemma, which I am going to leave as an exercise in the last slide. Okay, exactly this particular g by Schwarz lemma, you could have concluded mod gz is less than or equal to mod z, and you could have asked what is the meaning of that, and what you get as the answer is what is called Schwarz-Pick lemma. So it's a generalization of Schwarz lemma. It's a generalization of Schwarz lemma in the case alpha equal to beta equal to 0, right? If alpha is 0 and beta is 0, then G is F, no? Because phi at 0 is identity function, phi at 0 is identity function. So G will be F. So Schwarzschild lemma is a generalization of Schwarz lemma by arguing with such a G. Anyway, here we are taking the other part. So you get mod G prime 0 is less than or equal to 1. And what is G prime 0? You can apply chain rule. So you do this check that G prime 0 will be phi beta prime at beta times f prime alpha times phi minus alpha prime at 0. What you have to do is write down the chain rule. G prime at z will be phi beta prime of this of z times this prime of z. Apply chain rule once again. F prime of this of z times this prime of z. Put all that together, you will get this. Okay, so I'm skipping the verification. You do that, so you will get G prime 0 equal to this. But you can write down what is phi alpha and phi beta given by formula. So you can write down what these two derivatives are. So you check. So it's straightforward to check that phi alpha prime 0 is 1 minus mod alpha square, right? You know the formula for phi alpha prime. Phi alpha, therefore you have a formula for phi alpha prime. Check at 0. So you can check that this is 1 minus mod alpha square and phi beta prime at beta is 1 by 1 minus mod beta square. So what you are getting here is 1 by 1 minus mod beta square times f prime alpha times 1 minus mod alpha square. So you are getting 1 minus mod alpha square divided by 1 minus mod beta square times f prime alpha modulus is less than or equal to 1. So you have got a bound for mod f prime alpha. So modulus of f prime alpha times 1 minus mod alpha square by 1 minus mod beta square is less than or equal to 1. Therefore, you conclude that mod f prime alpha is less than or equal to 1 minus mod beta square by 1 minus mod alpha square. So this is quite remarkable. This is Rudin's next paragraph. It's quite remarkable because without any further condition, just from this much, you have the behavior only on you. You don't even know the behavior on the boundary of you. You have holomorphicity on you. You have boundedness on you, and therefore you take the supremum. You assume that supremum is less than or equal to 1, and you have this information that it takes alpha to beta. From that, you have bounded the value of f prime on alpha. You have got a bound f prime alpha bound in terms of beta and alpha. F takes alpha to beta, and that's the only information that is required in order to bound f prime alpha. So it's quite a beautiful result. And Rudin remarks that this kind of an argument will come in the proof of Riemann mapping theorem. So we will see next time. Next time or next to next time. Next time we will start the proof of Riemann mapping theorem, and either in that class or in the very next lecture, we will see this kind of an argument being used in the proof. But I hope this proof is clear. Okay, so you are getting a bound, and we are going to use this extra fact in order to classify. So what have we done in the previous slides? We have shown that phi alphas belong to odd U, right? Odd U, automorphisms of U, biholomorphic maps on U. Automorphism meaning a biholomorphic map on U. Holomorphic, bijection, inverse is also holomorphic. Inverse is holomorphic is automatic because it's a bijection, it's 1 1. Therefore, inverse is holomorphic is automatic because 1 1ness gives you derivative is never vanishing. So, inverse is automatically holomorphic. Inverse function theorem. We have shown that phi alphas belong here, and now we are going to show as an application of this bound, we will use this. So this already uses Schwarz's lemma, and as an application we are going to show that if f belongs to odd U, f is more or less a phi alpha. Okay. So before that, let me make this observation. If equality holds here, you can conclude something more. Why? Because this was just Schwarz lemma, right? This was mod G prime 0 less than or equal to 1. So if equality holds there, then equality holds here. And if equality holds here, what can you conclude? In Schwarz lemma, if equality holds, you can conclude that Gz is lambda z, where mod lambda is 1. Right? In Schwarz lemma, we have shown that if equality holds, then Gz is a constant multiple of the identity function. So using that, here if equality holds, Here if equality holds, right, you get this bound, and if equality holds, you can conclude that this function is a multiple of the identity function. This function g of z equal to z, lambda z. But what is f? F of z is phi minus beta composed with g composed with phi alpha. Right? Phi minus beta composed with g composed with phi alpha is f. So what can you say about f of z? You know that g of z is lambda z. So you will get phi alpha of z. Then g of phi alpha of z is lambda times phi alpha of z. And then phi minus beta of that. So you will get, from that you will get, if equality holds here, then equality holds there. And from that you will get fz as phi alpha of z. Then g of phi alpha of z is lambda times phi alpha of z. Then phi minus beta of lambda of phi alpha of z for some lambda in C. This much you will get by Swaziland. Okay, so we have proved a very nice result that you can bound mod f prime alpha in terms of what is f of alpha. If you call that beta, then this is the bound. Not only that, if there is an equality here, this is very crucial in our next slide. If equality holds here, then you can conclude that fz is of this form. So if you have an arbitrary function which is holomorphic on U, norm is less than or equal to 1, and if it takes alpha to beta, then you know it cannot be arbitrary. It is in terms of phi alpha and phi beta. If f takes alpha to beta, then f has to be of the form phi minus beta composed with phi alpha, except for this twist in between, except for this dilation in between. So it's very, very beautiful. Yeah, no, sorry. I'm not saying that any f has to be of this form. If f is of that form that f is on U, norm is less than or equal to 1, it takes alpha to beta, then you have a bound for the derivative at alpha. And if this bound is attained, then f is of this form. If equality holds, if the bound is attained at alpha, mod f prime alpha equal to this, then f is of this form. You know, it is in terms of functions that we very well know, Mobius functions, certain rational functions. Okay, this is what we are going to use. Now suppose f is an automorphism of U. F is in HU, f is 1 to 1, f is on 2, and alpha is some element in U such that, and f of alpha is 0. Suppose you have an element such that f of alpha is 0. Now there will be an element alpha, no? Why is this true? This is automatic. This you don't have to assume. There is an alpha in U such that f of alpha is 0 is given to you. Why? Why does this follow? Can I? Oh, okay. I did not know this till now. I can project. So why does this follow? I'm saying this follows from these conditions. Yeah, I think I remember you are trying to say something, but I can't. F is on 2. I can't hear because you know my sound was not full. Yeah, because it's on 2, right? F of u is u, 0 is here, so there is some alpha such that f of alpha is 0. So pick one such alpha. And how many such alphas are there?
1.
Exactly 1, because f is 1, 1. Okay, so there is a unique alpha such that f of alpha is 0. So pick that alpha. Okay. So now we are in good shape. Let G be the inverse of f. Why is there an inverse? Because whatever we recalled. Because f is 1, 1, f is never vanishing on U. And if f is not vanishing, then there's a neighborhood on which you know that the inverse is holomorphic, but f is never vanishing. So every point has a neighborhood on which G is holomorphic, and therefore G is holomorphic on U. So G is the inverse of U because f is a bijection, and G is holomorphic because f is 1, 1. F prime has no 0 in U, therefore G is holomorphic, right? If inverse function theorem will say that if f prime is not vanishing, there is a neighborhood on which the inverse is holomorphic. But that applies throughout because f is 1, 1, it has the derivative is never vanishing. So every point has a neighborhood on which G is holomorphic. So G is holomorphic throughout. So G is in HU. By chain rule, so what does this mean? G composed F is identity. So G prime of Fz times F prime of Z is 1. G prime of Fz times F prime Z is 1 for all Z. Take Z equal to alpha. So G prime of Fz, F of alpha is 0. G prime of Fz times F prime of Z, Z equal to alpha. In particular, you get G prime 0 times F prime alpha is 1. Agree? Therefore, you have mod F prime alpha is less than or equal to 1 by 1 minus mod alpha square. Why does this follow? No, not therefore of this, not because of this. Anyway, you have this. Why is that? Because if F takes alpha to beta, then you have a bound for F prime alpha. If F takes alpha to beta, then mod F prime alpha is less than or equal to 1 minus mod beta square by 1 minus mod alpha square. That is the previous slide. So this is 1 minus 0 by 1 minus mod alpha square. You have this. You also have this by the same argument. G of 0 is alpha. G of 0 is alpha. G is the inverse. So G of 0 is alpha. Therefore, mod G prime 0 will be less than or equal to 1 minus mod alpha square by 1 minus mod 0 square. So both of you get both these from this identity that we have proved. From this identity. From this identity we have proved by taking alpha and beta to be 0, you get one of those, and taking alpha to be 0 and beta to be alpha, you get the other one. So you get both these from the previous identity that we have proved. Now you use this. This you haven't used yet. This is an observation that we have made. What can you conclude about these inequalities because of this identity? What can you conclude?
That equality is holding in the
Yes.
original thing.
In both these inequalities, equalities hold because the product is equal to 1. Therefore, this has to be an equality. Oh, this is good that I can, highlight. I forgot that I can do that. Instead of putting cursor, I can highlight now. So this is an equality. This is also an equality. But go back to the previous slide. You have this inequality, and then we concluded that if equality holds, Fz is of this form. And we have concluded that equality holds. Therefore, Fz has to be of the form phi minus beta lambda phi alpha. But what is the property of F? F of alpha is 0. So beta is 0, alpha, and beta is 0. But phi 0 is identity function. So Fz is lambda times phi alpha. So because equality holds, you can conclude that, in fact, you don't need this. You don't need this. You need only this. Yeah. So I will delete this. That's unnecessary. So because of this equality, you conclude that beta is 0 here. So you conclude that phi minus beta of this. So that is lambda phi alpha z for some lambda in C. And yeah. So this is so you have characterized.
That lambda will have modulus 1, right?
I was just thinking, is that that follows, no? Yeah, it follows, right? Why? Because
That's what Schwartz theorem had told us, right? Schwartz lemma.
Schwartz lemma will say that so you are using the fact that f prime 0 is f prime 0, you have equality. No, you can't directly apply, no? Because there, the function.
I mean, in the previous part also.
So we just have to check it here. Yes. We just have to check it here for some lambda in C. So you are saying here also mod lambda is 1. Yes, that's correct. Because this was from Schwartz. The proof of this is Schwartz lemma here. Equality holds. Equality holds here. Therefore, Gz is lambda z with mod lambda equal to 1. With mod lambda equal to 1. Therefore, here it is mod lambda equal to 1. Yeah, I should write this. I should write this. So, for some lambda with mod lambda equal to 1 by Schwarz lemma, and this is exactly that. Therefore, this is also true with mod lambda equal to 1. Thanks, Adiman. I will add that. We get this with mod lambda equal to 1. It's not clear from this final output, it's clear from the proofs that mod lambda is 1. So, we have characterized OTU, right? You have taken any f in OTU. That means this much is given, and then you have shown that f is of the form phi alpha essentially because up to a constant multiple, and that constant also modulus is 1. Okay, so you have characterized OTU as a corollary to Schwarz lemma. Okay, so the next slide is Schwarz-Pick, which says that if f is in HU, then for all alpha beta in U, you can get f alpha minus f beta. No, f is in HU is not enough. You need all these conditions. Whatever conditions I needed here. Suppose f is in H infinity and norm less than or equal to 1. You don't need f alpha as beta, that's not required. You assume that f is in H infinity with norm less than or equal to 1. That much you assume. So f is in, so that also I have to change. So if f is in HU and norm f less than or equal to 1, I think you have to assume. Then if you take alpha beta in U, then f of alpha minus f of beta by 1 minus f alpha bar f beta is less than or equal to this, mod alpha minus beta by 1 minus alpha bar beta. So how will you do this? If you have given alpha and beta, how will you do this? You take, yeah, it needs an argument. What you do is you take, yeah, so maybe notation was not very good here. Yeah, what you can do is, you come to that situation where we argued with G, where f of alpha is beta. So you can argue with alpha and f of alpha and take the corresponding G and argue with that. You need to think a little bit. So you think about it, otherwise so this was not stated in Rudin, or maybe it's an exercise in Rudin, but the Wikipedia page of Schwarz lemma has exact this statement. So you think about it on your own. I'm leaving it as an exercise. It is about constructing a G and applying Schwarz's lemma for G. That G you have to construct appropriately. And if you can't do it, you can refer to the Wikipedia article where there's a very nice 2-line proof. So you just have to consider the correct function. And Schwarz lemma has two parts. One part is mod fz less mod gz less than or equal to mod z. If you take that, you will get this. The other part is mod g prime 0 is less than or equal to 1. If you appeal to that, you will get this. So both these are generalization of Schwarz's lemma by taking an appropriate function by composing 3 times, and this is called Schwarz-Pick. Okay, so this I'll leave it as an exercise. Try this. So we will stop now and start the discussion session where if you have any questions we can discuss, and stop 20 students. Let me stop the recording.